It's a great day for Gauss-Bonnet. We're back after a brief hiatus here. Today we're going to talk about a paper of Erickson and Whittlesey to determine if a curve on a surface is contractible or not. And we're going to use the Gauss-Bonnet theorem to come up with a pretty cool algorithm. Let's dig in. All right, we're up to video 8. And I'm Brad McCoy. We're into December 2023. All right, so last time we talked about Gaussian curvature, discrete Gaussian curvature again, and we came up, so we used the Gauss-Bonnet theorem to come up with this formula where alpha I is the angles incident to a vertex. So we have here, this would be alpha 1, say, alpha 2, and so on. And we found it was useful to consider the complementary angle. And this gave us another formula for the discrete Gaussian curvature, which we saw was exactly the area of a polygon on the sphere. So that was a nice thing to notice. And then we used that to prove the Gauss-Bonnet theorem for triangulated surfaces. First, we proved it with no boundary, and then we used that proof to consider the case where we had some boundary there. So that was last time. Agenda, today we're going to look at homotopy testing on surfaces, and particularly if we're given a surface and we have a curve on the surface, we want to know if we can contract that curve to a point continuously. So that's our agenda, and we'll see sort of a new version of the Gauss-Bonnet theorem. I don't know if this is even accurate, but we'll see we'll call it a new version of the Gauss-Bonnet theorem. Did we get any feedback? No, not really. The number of views is continuing to increase, so that's exciting. But I'd like this to be a more, involved segment of the talk is what is the feedback. So again, I can take criticism if it's given in a constructive way. So if you have some constructive criticism, feel free to leave it in the comments, and we'll address it. I want to improve the videos if possible. Okay, so what are we doing today? Homotopy testing. So we're given a surface. So here we see genus 2 surface, and we have a curve on the surface. So maybe our curve is looking something like this. And we want to know, can we continuously deform our curve to a point? So this curve, I would say yes. You can just say continuously deform it to that point. But what if I had this blue curve here? If I tried to continuously deform that curve to a point, I would get stuck around this hole in our surface there. So some curves you can contract to a point, and some curves you cannot, based on the topology of the surface. And we would like to come up with an algorithm to determine which curves have this property that you can continuously contract them to a point. Okay, I first heard about this in a paper by Erickson and Whittlesey, and that's from 2013. And then Jeff Erickson has some video lectures. I watched the 2020 version, but I think he has an updated version on his website. So if you want more info, you can read the paper or watch his videos. His videos is like an hour and 15 minutes, where I'm trying to do this in approximately 20 minutes. And this goes back to Max Dane in 1911. And again, Jeff Erickson talks about that in the videos if you want historical perspective. Okay, so we're talking about, give me a curve on a surface. Can I contract that curve to a point? And we want an efficient algorithm to answer that question. So you might ask, well, what is a curve? Well, we have a triangulated surface, and we can think about, well, maybe our curve is going around like this or something. And we could say, well, our curve, we could represent it as a sequence of, in this case, it would be faces and edges. So I'm hitting this face, then this edge, then this face, then this edge. But there's a couple different ways to think about this. You could think about it in the dual, where we represent each face as a vertex and each edge is still edge. So then we get a sequence of edges and vertices. Or we could snap our curve to vertices and edges as well. So maybe here we could say, well, we're just going to go like this, and maybe now we're up here. So some sort of snapping happened to get from this red to this blue curve. Okay, so curve, and now I have alternating sequence of vertex, edge, vertex, edge, vertex, edge. Oh, Murphy's wilding out over there. Murphy's my dog if you didn't see the other video, but he's being a little bit disruptive. Bad dog. Okay, so we're talking about this continuous deformation, and so we're saying, what is that? That's a homotopy. So we have continuous deformation. So think of homotopy, continuous deformation. So if we have our curve and I want to know, can I contract it? We're going to continuously deform our curve. And that's an example of a homotopy. So there we go. Okay, so we want to discretize a homotopy. So we're going to have some homotopy moves. Our first move is going to be a face flip. So if I had a curve that went something like this, I could update it and say, well, don't go the long way around this face, just take the shortcut. And so this is a face flip. We could also do an edge spike. So instead of going here, I could go up and back. And so that would be an edge spike. And then we could do an edge unspike is the inverse of a spike. So we could do all these moves, and that represents a continuous deformation in a discrete version of continuous deformation. So that's our homotopy. So now we're back to restate our problem. So we're given a walk in our surface, and we want to know, is there a finite sequence of moves? And by moves, I mean these three moves, face flip, edge spike, edge unspike, that reduces the curve to a trivial walk. So I'm given a curve like we see here. Can I reduce it to just a point is my question. So here the answer would be no. All right, so our first move here is going to be to simplify our surface. And we're going to do this by removing edges and vertices until we're left with just one face, one vertex, and 4 G loops. So algorithmically, you can do this by finding a co-tree decomposition of our surface, and then we're going to contract the tree. So this will be contracted. So this we want to contract. And then we'll remove edges and vertices in the co-tree. And then we'll be left with each edge that remains is non-contractible edge, and we can represent our surface in this way. So there is a face here. So our first move is simplify our surface, and we're given a curve on our surface, so we're going to have to simplify that as well. And we can do this in a nice way. So if there's an edge and we remove it, we can just remove it from our walk, or if we contract it, we can contract it in our walk in a nice way as well. So we're going to end up with one vertex, degree 4. So here we're seeing all these vertices, but really they're all the same vertex. We have one face, degree 4G. Here you see that in here. And we have 2G loops. So we get these sort of mapping information that represents the 2G loops. So step 1, simplify our surface into what Erickson calls a system of loops. And this can be done by a co-tree decomposition. And then, as I mentioned before, we also simplify our curve. So if we have, say, our curve, let me get a color I'm not using, went across maybe like this, well, we could snap it to one side. So maybe we'll take the shorter way around. And so we're adding at most 2G edges. So we still are, if we have a walk of length L, in our system of loops, which is another name for our simplified surface, we're going to get W prime, and it's going to have O of GL because I'm doing this snapping. And our surface is going to go from N down to G, which is often a tremendous simplification. Okay, so we simplified our surface, simplified our curve as well. So the next fact we're going to need is from algebraic topology. We're going to think about the universal cover of our sort of, what are we going to call this, cut and paste diagram. And so if we just have the torus, we can cut two cuts. So maybe cut around here and then cut around here. Oh, nope, don't do that. And then cut around here. And then we could turn this into a rectangle. And we can think about, well, putting copies of this rectangle together to get our universal covering space. And the things to note here is we can't tell the edges apart. So if I'm here or here or here, I don't know really where I am exactly. Or all these vertices, if you're walking around, there's infinitely many of these vertices, I don't know exactly where I am. Okay, so hopefully you've seen that before. I'm not going to spend too much time, but we have a lift to the universal cover happening. And if we have a genus G greater than 2, we're going to get some hyperbolic geometry. So instead of this nice grid, we get sort of this Poincare disk model. But no, the same idea just happens, as you can imagine, just walking around here, and that corresponds to walking around on our surface. And the same thing happens here, but with sort of this more exotic geometry. And the big fact we want to use here is that our curve is closed in the universal cover if and only if it's contractible in the surface. So let's look at that happening. So if we go back to our torus example, if I go, let's say I went this way, that is not closed in the universal cover. And what would that mean? Well, that would mean I'm going around this loop, and that is not contractible. Whereas if I had a closed walk, what would that mean? Closed in the cover. Well, that would mean I went around here once, and then I went, oop, it snapped there. So I went around here once, and then I'm going, so I went this way originally, and then I'm going back around here, and back, oh, what's it doing? And then back around here, and that would be contractible. So hopefully, if you hadn't seen this before, I know this is a big ask, but if you've seen some algebraic topology, this is like a really cool thing. So contractible in our surface, if and only if closed in the universal cover. And so now our problem becomes, we can consider the universal cover and determine if we have a closed walk. Okay, but our walk looks sort of funny. So you might think, well, if we have a walk in our universal cover, can we just look at the end and see if we're back to where we started? But when we did this system of curves reduction, we're losing a lot of information. So our walk just looks something like this. So we take these exits and we want to know, so if each intersection looks like this, and we take, intersection 2, oh, let me keep my color scheme going here. And then we take go direction 4, and so on. You can't tell just by looking at this thing if it's a closed walk. So our idea is going to be, we're going to remove spurs and parts of the curve where we stay on the boundary of a single face for most of the way around the face, and we'll keep simplifying our walk until we either end up with the trivial walk, in which case our curve is contractible, or we can't reduce it any further, which indicates that we're stuck around one of our essential loops here. So that's the idea, and this is called Dane's lemma. So we're gonna, if we have a closed walk, so this is in the universal cover, well, then it either has a spur or 4g minus 2 edges on the boundary of a face. So what would that look like? So if we have our octagon representation of the genus 2 surface, well, that would mean we have almost all the way around the face. So we can do this face flip, and instead of going the long way around, just take the short way around. And we've shortened our walk, and then we can try again to shorten and continue to try to shorten until we can't shorten anymore, or we've gotten down to the trivial walk. What did I want to say? Oh yeah, so we're only considering the genus is greater than or equal to 2. If the genus is 1, then we have the torus, and there's some other things we can do, so higher genus surface. All right, the Gauss-Bonnet theorem that they used here looks a little bit different than what we've seen before, but we can verify quickly that it really agrees with what we saw. So here you can assign an arbitrary real number to each corner and define the curvature of a face to be 1 minus the sum of the values on the corners, and the curvature of a vertex to be 1 minus 1/2 the degree plus the sum of the values on the corners as well. And we want to check that, is this really a Gauss-Bonnet theorem? Well, we could check that it adds up to the Euler characteristic, and that's can be done quite quickly. So if we add up our curvature of a face over all faces, we're going to get the number of faces plus, and we're going to hit each corner exactly once, so we get all of our corners here. And if we add up our curvature at a vertex, well, we're going to get our number of vertices, our degree. Each vertex has, each edge has 2 vertices, so we get our edges, and we get, again, the sum of these numbers over every corner. So if we add these together, these values cancel, and we exactly get our Euler characteristic. So this feels like, aren't I just rewriting the Euler characteristic in sort of a funny way? And yes, we are. That's what the Gauss-Bonnet theorem is saying. So that's sort of interesting, that this is a version of the Gauss-Bonnet theorem that seems like, oh, you're just adding and subtracting the same thing. Yeah, that's what the Gauss-Bonnet theorem says. And you get the Euler characteristic. So we saw our previous versions of the Gauss-Bonnet theorem also sum to the Euler characteristic. So therefore, this is an equivalent variation. Okay, so when we lift, I'm going to draw my rectangle or my octagon one more time. We can, in this hyperbolic geometry model, we can force every angle to have a value of 1/4. Oh, yeah. So here we're not talking about angles in terms of 2 pi. We're just saying what proportion of the circle did we go around. So this, when I say 1/4, this really means a 90-degree turn. So hopefully that's not confusing. Okay. So then we look at what happens on our curve. So each face has degree 4g. Each interior vertex has degree 4g, and each boundary vertex has degree less than or equal to 4g. And so if we use our definition of curvature of a face, we see, okay, we have 4g corners. Each one has value 1/4. And so if we add those up, we'll just get g. And the important thing to note here is this is negative. And the same thing for interior vertices here. We're going to get 1 minus g, which is also negative. If we look at boundary vertices, we have 3 flavors. So we could go, we could have a convex vertex. So that means we go something like this, make a turn here. And here we see, well, we're going to have degree 2 and our 1 corner. So these will cancel, and we have 1 corner, so this will give us a 1/4. If we go straight across, what are we going to get? We're going to get 1 minus 3/2 plus 1/2, so that's going to give us 0. And if we have a concave vertex, we're going to get something negative. So again, you could work that out. But we'll get a negative value. So that's the important thing. And so we can use our Gauss-Bonnet theorem. So this is, let's make a big deal out of this. So this is by Gauss-Bonnet. We're looking at the interior of our walk in the universal cover. So that's going to be a disk. So we get Euler characteristic 1. Then we're looking at the sum of the curvature of each face. Well, we saw above that that's 1 minus g. And so, I'm getting ahead of myself here. So we're going to get the number of faces times 1 minus g. And then let's only consider our convex vertices. The other ones are negative or 0. So let's say we're dropping negative things. So we're making the left-hand side of this equation bigger. And so by our Gauss-Bonnet theorem, that tells us that our number of convex vertices is bigger than this quantity. In particular, the expected value of our number of convex vertices is greater than 4g minus 3, which tells us there has to be at least one convex vertice, or at least one face with 4g minus 2 convex vertices. So this is sort of our big takeaway here. Let's emphasize that. And what does that look like? Well, that looks like we're taking the long way around a face, something like this. And so what's our algorithm look like? We start with our walk that is maybe stored in some sort of array. And we look at instances where we have a spur, so that would be like an out and back, and we reduce that if we see a spur. Or we have these faces that go the long way around, and then we can update by taking a shortcut by flipping the face. And then again, we shorten as well. And we see at the end of this process, do we end up with a trivial walk, in which case we have contracted our curve to a point, or do we end up with something that can't be shrunk any further, which tells us that we can't do any more of these moves and we have no more spurs, and that tells us that our curve must not have been contractible. And so this algorithm is very cool, and it gives an O, n plus L, so this is the complexity of our surface, and this is the complexity of our curve, time algorithm to determine if we can contract a curve to a point on a surface. So nice application of the Gauss-Bonnet theorem. And we have this nice Dane's lemma that tells us about the existence of this face with where we walk most of the way around the boundary and we can simplify. Okay, thanks for tuning in. It's a great day for Gauss-Bonnet. Is a curve on a surface contractible? Gauss-Bonnet theorem helps us answer that question. See you next time.